So we're going to do one more Gauss's law example. And this time we are going to look at a cylinder. And we're still looking for the electric field on different intervals throughout the cylinder. So let's get started. First, what are we looking at? We've got empty space from 0 to R1, and then a conducting cylinder from R1 to R2, more empty space from R2 to R3, and then an insulating cylinder from R3 to R4. Now this conducting cylinder has a charge density of sigma, and again the sigma is just charge per area. This row up here is charge per volume. Now this is really what we're looking at. We've got the cylinder. We can just pretend it goes on forever, or just has a length of L, whatever. And here's the conductor in blue, insulator in red. Let's get into the problem. We can just write Gauss's law as always. E dot with the A equals charge enclosed over epsilon naught. Now remember, for the surface integral, we just have to say magnitude of electric field times the surface area of the shape we're talking about. In this case, we've got a cylinder, so we're just going to do perimeter of a circle times length, so that gives us 2 pi r L, still equal quank over epsilon naught. Then finally, the formula we're going to use for the whole problem, Q E and C over 2 pi r L epsilon naught. So now part A. When 0 is less than R is less than R1, this is the radius. This little r is the radius of the Gaussian cylinder. So when a Gaussian cylinder has the radius from 0 to R1, what is our electric field? Well, this is our formula right here. And in this case, Q, E, and C, what are we enclosing? From 0 to R1, we are not enclosing anything because it's just empty space. Q, E, and C equals 0. Therefore, the electric field is going to be 0 vector because there's no charge enclosed, there's no electric field. Super easy. Now part B. R1 to R2. Now what is from R1 to R2? It's a cylinder conducting. Okay. So now remember also, the electric field inside a conductor is always 0. So this one, again, electric field equals the 0 vector because conductor. Nice. If the interval is ever inside a conductor, it's always 0. Now we can get to the real parts of the problem. So part C. What are we doing? R2 to R3. Now when the Gaussian cylinder has a radius between R2 and R3, the only charge it's enclosing, if this was the Gaussian cylinder on some point little r between R2 and R3, the only charge it's enclosing is due to this charge on the conductor. Now the conducting cylinder is only going to have charge on this outer surface. That's why it is surface charge density, because it only exists on the surface. Now, to get our charge enclosed, we need to think, okay, we have sigma, we know sigma is charge per area So our charge is just sigma times the area. In this case, the charge is just sigma times the area on which the charge exists, which is looking like this. R2 is how far it is. And then you just do the surface area of a cylinder with R2. Surface area of a cylinder is 2 pi r times L. So we're going to use R2 times L. So that will be our charge enclosed. Now we plug that into our formula. Q and C over epsilon naught, which in this case, 2 pi RL epsilon naught sigma 2 pi R2L over 2 pi RL. Now we can see this stuff is going to cancel. Now our vector is just sigma 2 pi cancels out, L cancels out. So sigma R2 over R epsilon naught times R hat, because we got rid of the magnitude. And yeah, that looks right. So B, what is B? We're going from R1 to R2. Okay. We're not doing B, we're doing D. D. R3 to R4. Now, in this case, our Gaussian surface, our Gaussian cylinder is somewhere between, the radius of the Gaussian cylinder is anywhere between R3 and R4. So we're going to write an equation that represents the electric field of the Gaussian cylinder on any radius on this interval. So now again, we're doing our charge enclosed as always. Q and C. Now we're still enclosing the charge from this conductor. So first we can just copy down that same exact charge. This charge is still going to be the same. So it's going to be sigma 2 pi R2L. But now plus however much charge we're now enclosing from this insulator. So that's going to be the volume of this. Remember, if we have rho, Q equals rho times volume. Just like Q equals sigma times area, Q equals rho times volume. So how much volume are we having? For example, if we're at like a radius of here, this would be our little r away from the center minus R3 would get us this, and that would be this length. So how that would look in the equation is we would just say we're going to multiply our rho times the volume of a cylinder is just the area of a circle times the length of the cylinder. So our outer radius will be pi little r squared minus the inner radius. The inner radius is R3. Outer radius, how far away we are. We're r little r away. Minus, it's always defined as R3. So pi little r squared minus pi R3 squared. This is supposed to have an L. Okay, now it makes sense. Pi r squared L. Okay. Now we have that. We can just plug it into our formula. 4 pi r squared epsilon naught, which equals 2, I'm going to write it like 2 pi sigma r2l plus, factor out these guys, we're just left with r squared minus r3 squared. For pi r squared epsilon naught. Now to get our final answer, remove the magnitude. Now what can we cancel? Pi goes away. Oh, okay. See, I used, this is wrong. I used the surface area of a sphere, but did I do that before? No, we're good, we're good. Okay, cylinder is always 2 pi r l. This is still 2 pi r l. Pi still cancels. L, L, L. And that looks good. So now E equals 2 sigma R2 plus rho R squared minus R3 squared divided by 2 epsilon 2r epsilon naught. Add your unit vector r hat, and that will give you that answer. Now our final part is from r. R is greater than r4. So now we're saying this Gaussian cylinder has a radius greater than r4. Same process. What is the charge enclosed? Well, we're still definitely enclosing the sigma charge from before, and we're enclosing now all of this rho charge. The only difference with this charge enclosed from the last one is that it doesn't matter what our little r is in this case, because our little r is always greater than r4. It's always going to be beyond it. Therefore, instead of how we did here, where we did little r squared minus r3 squared, we can now have this as a defined r4 minus r3, because we're going to be enclosing the entire thing, not just some portion of it depending on our little r. So we can write the charge enclosed is still sigma 2 pi r2l plus rho times pi r. Now it's r4 squared. It's no longer little r, it's r4 squared. My times l still. Minus pi r3 squared times l. Boom. Write your equation. Magnitude of electric field equals Q, E, and C over surface area times epsilon naught. Plug that in and you'll get 2 pi sigma r2l plus rho pi l r4 squared minus r3 squared divided by 2 pi rl epsilon naught. Again, we can cancel pi, cancel l. Now, oops. Okay, final answer for this part would be electric field equals 2 sigma R2 plus rho R4 squared minus R3 squared divided by 2R epsilon naught add unit vector R hat. And that's good for the electric field. And that puts an end to Gauss's law for the cylinder.